this time. So are we live, Richard?
We are now live on YouTube.
Wonderful.
Okay. Welcome. People should kind of come in over time. I know some coming. Welcome to the first newish Saito Social. We have done this in ages.
Yep.
Our guest today is Dan from Radix, and I'm really excited because we've known about and we've followed Radix for a while, and we have a chance to ask Dan some utterly stupid questions and learn more about atomic composability and what Radix does. So Dan, thank you for being here.
No worries,
since it's our first time, I was just gonna, since it's our first time, just point out that our goal here is actually not to talk about Saito, to actually talk about Radix. We're supposed to have an announcement this week about the latest Saito summer drop. That's not what this is. What we're hoping to get out of hosting Radix and in the future other projects is really just create a space for people to talk about fundamentals and try to get more exposure of the different approaches and the different things that are happening in crypto, to try to give some pushback against, you know, the marketing and the shit coining and all of this stuff where, you know, meme coins in this, and try to get some attention to the people that we know who are doing serious, important work. So that's what this is. Before we start to waylay Dan with questions, you have anything you want to chime in on?
Yeah, I suppose it's probably good to start with a little bit of Radix background, right? For your listeners who maybe don't know what Radix is, or at least the story. So I've been in crypto a long time, well over a decade now. And like many of us from the early days, we were very interested in Bitcoin for one reason or another. My initial interest was, how has somebody solved this Byzantine generals problem in a non-centralized way, right? That was like, holy shit, this is huge. And initially I wanted to understand that solution, which, you know, my opinion is very elegant. And then got an appreciation for, you know, the kind of cryptocurrency economic aspects of Bitcoin, you know, so not just disruptive from a technological perspective, but also potentially very disruptive from an economic perspective as well. And spent a bunch of time digging around in Bitcoin and doing, you know, nerdy things, taking it apart, playing around with it and stuff. But kind of came to a conclusion that if this technology is so disruptive from a tech and economic point of view, then there's potentially some roadblocks, right? The main one that everybody's aware of is obviously scalability, right? But then you've also got, you know, centralization, things like decentralize over time, and especially with Bitcoin's economic model, it kind of promotes that a little bit. Things like price volatility and the user experience, developer experiences, all these things, right? So initially I was thinking, you know, I'll get involved in the Bitcoin project and try and find some solutions to some of these problems. But then, you know, after a few months of doing that, really came to the conclusion that this protocol is kind of hard baked now. It's going to be very difficult to make any large changes, you know, pushback from the community and stuff. So maybe a better option is to just kind of, you know, new file and try and solve some of the problems that I expected to come down the line, which most of them have, you know, 10 years later in hindsight, and try and solve some of those things to make a better solution that potentially could onboard billions of people and billions of devices and DeFi and all this stuff, right? But maintain those critical ideologies of Bitcoin, you know, permissionless and decentralization, self-sovereignty and all that stuff. And obviously I grossly underestimated how long that would take. Which you guys being techies, well, we always underestimate things grossly, right? And then we realize that shit, I've maybe bit off a bit more than I can chew here. And so that's kind of where my journey and Radix started, was, you know, 2013 or so. How do you scale? And had some good solutions early on, test nets, tested with the community and stuff, where we were seeing 2,000 or 3,000 transactions a second, which for 2013, 2014 was insane, right? But it kind of dawned upon me that that's probably not enough. Actually, at the time, everybody was visa scale. If we get visa scale, we'll be good.
It was always the metric,
it was a benchmark metric, right? If we get visa scale, then we can take over the world, kind of attitude. And then we got to visa scale, and at this point, I kind of realized that this is nowhere near enough, actually, right? Because you've got Visa, you've got MasterCard, you've got online payments, you've got all of that. If you just count the kind of B2C, business to customer stuff, you probably need 15,000 or 20,000, right? And then if you think about over the long term, internet connected devices, IoT, AI in the very far future, which is obviously what I'm talking about now, right? AI is starting to become a force. And I kind of came to the conclusion that actually what's more likely to happen is that blockchain and similar technologies will be a conduit between all of those things, right? So you'll have all of your users and all of their fridges and toasters and cars and whatever else, and AI and all these things. And then, you'll have like interesting complex transactions, which is now known as DeFi, right? Stocks, trades, real world assets, all this stuff. Like if this thing really actually takes off in the way that it can, and you potentially need hundreds of thousands, if not millions of transactions a second of capability over the long term. And so that's kind of when pivoted from let's make an incremental improvement to let's actually make a leap, because this is going to be a long play at this point now. And how do you solve for millions of transactions a second, but also retain decentralization and security and all the other nice things that we want to keep, right? And that's then the major journey that led to Cerberus and the Cassandra test network, as you guys, I no doubt, have seen me post about, where I do a lot of testing for Xi'an, which is the next network iteration, and really prove out that the only way to do this is linear scale. Add more computers, the network grows, then it scales linearly, so you don't hit a plateau. In the same way that the internet is linearly scalable, right? And it's decentralized, and an advantage that the internet has, of course, is that it's stateless, whereas this is a bit more tricky when you've got statefulness. And then, so how do you solve for all those things? And then the additional piece on top of that is, as I'm sure you've all heard this term, is then atomicity, right? That's atomic composability, which is a rabbit hole into itself, because it's very misunderstood what that term actually means and how difficult it is to solve for in a kind of realistic way, right? So yeah, that's kind of like my monologue of the journey and where we are, and why I've gone grey and got wrinkles.
Where in that did you hit on sharding?
So I was looking at sharding very early on, actually. So at the time when Vitalik was writing the Ethereum Yellow paper, it was around that time I started to think about sharding, right? But then, obviously I know about sharding techniques from distributed systems in the past that I've worked on in databases and stuff. But one thing that I didn't actually want to do was just put all my cards into sharding prematurely, because my thought process to a degree was, this is a new kind of technology, so maybe there's a different, better, more efficient way to scale these systems than just going with the trial or tested sharding approach that you would find in distributed databases. Right? And at this point, it was kind of obvious that this was going to be a committed long-term play. So I wanted to investigate other avenues to be sure that I wasn't just blindly discarding something that maybe would be a better solution. So there's a few years there just going around the neighborhood trying a bunch of different things, and every iteration just got me closer to sharding. Right? It's like, okay, so I need to handle this. So what does this architecture look like? Okay, that stepped a bit more towards sharding, and then by like the third iteration, it's like, you know what, screw it, let's just go sharding. Right? It's obviously sharding.
Can I pull us back to Atomic? Because we've got Richard and I think for us, the interesting thing chatting with you and the opportunity to ask you questions too is interesting, because we're coming from an odd place in that obviously Saito is, it's single thread. Maybe it can be sharded in the future, maybe through L2 bridges and that sort of thing. The result of this is that atomic composability is actually the thing that I associate with Radix the most. So I do, before we talk about the rest, it might be useful just to mention this. Sure. We have questions that are a mix of complicated and non-complicated. And interestingly, some of the questions we have are just not complicated at all, because I think we understand atomic composability, but maybe it's good to start with this. My understanding is that the user makes a transaction. You've got part of the kind of transaction compilation process, script, and the app layer is it breaks it into a series of instructions where it's going to know, okay, shard A and C and shard ZZD all need to approve this. And then you've got kind of vectors and quorum certificates that are produced as messages are passed around. And at the end of it, you have this giant bundle of digital signatures that can be approved or rejected by everyone in the network. And that this is really what Radix is doing that's new and special. Whereas other sharding systems, the shard handles the withdrawal. Could you just comment on this? I mean, am I wrong? Am I right? Where am I wrong? Anything?
So let's go like a bit top to bottom in terms of atomic composability, right? Because this is a term that's thrown around a lot, but there's a lot of myth and a lot of conflation, and it's not really understood, I think, what it actually is, right? And how you arrive at atomic composability. So I think the first thing to define is that atomic composability is actually two things, right? And atomic composability probably isn't the right term, but it's the term that everybody uses now. But really what you have is, if you've got true atomic composability, then you actually have atomic execution, where all the steps of a complex transaction, they either all complete or they all fail, right? So in the sense of, if I'm swapping a token across a bunch of pools, like pool ABC, right? Then if the swap from B to C fails, then I don't want anything to happen, right? I just want my initial tokens back, right? So you have atomicity in the case of the execution, where either everything completes or nothing completes. But then you also have, because we're talking about stateful systems here, you also have commitment, right? Okay, so the execution was good, but that doesn't mean that the state changes can be committed, right? So we now need to come to an agreement on commit between all the validator sets and commit all of these changes. And we also want that to be atomic too. So if, for example, shard X has a problem and can't commit the state changes that it's responsible for, then nobody should commit any of the state changes anywhere, right? Otherwise you get into all kinds of headaches, where shard B has committed something, shard X,
your money is spent, but
you get hanging.
Well, everyone but Phil understands that you've spent your money.
Yeah, exactly, right? You get all of these nasty edge cases and hanging state and state inconsistencies and all that stuff, right? So really, when you're talking about atomic composability in the truest sense, that's what you're talking about: atomic execution plus atomic commitment, right? Now, if you are a monolithic or non-sharded architecture, you essentially have that from top to bottom anyway, right? Because all your validators, they're all executing, they all agree to commit, and then they all commit the changes. Where it starts to get complicated is in quotes, sharded systems, right? So an L1 that is sharded at the protocol layer, or even if you've got an L1 base layer, then you've got multiple L2s that want to talk to each other, or like side chains, or all those kind of different systems where some state lives over here and some state lives over there. And then what you start to see, excuse me, I am recovering from a bit of a flu last week and I've still got the damn cough. So hence the mug of coffee. So with a lot of architectures, they don't have strict commitment, right? A lot of architectures have the atomic execution part done. Most, there are some that don't, but a lot of architectures don't have this strict synchronous atomic commitment. And so the issue there is that even though from the user or developer point of view, it looks and feels like true atomicity in both of those components, the reality is that behind the scenes, the protocol may be making changes before all of the parties that need to commit these state changes have committed them, right? So they make like a tentative change. Okay, I'm going to change this state, but I'm going to hold the lock just in case it doesn't go through.
Yeah.
And then Shardix fails. Shardix then has to send a message to everybody. Everybody then has to undo that state change, and then they can release the lock, right? So that's kind of like asynchronous atomicity, if you like, right? But it's much easier and much less complex, and I say that with a grin because it's been an extremely complex problem to solve. But in terms of, kind of on the ledger complexity, it's much better if everybody either commits at the same time or doesn't commit at the same time, as opposed to putting something tentative on ledger and that goes into a block and then you're waiting for a confirmation. But what if that confirmation doesn't come or it's late? Then what do? Do you time out and undo it anyway? But then you might get a message to say, yeah, I committed this. Okay, sorry, I was just a little bit late, right? And, I've got to commit it again, but I can't because something else has now happened, and you just get in a mess, right? So my opinion was that the only way to do this properly was synchronous commitment. You can have asynchronous execution where not all parties are synchronized on the actual execution piece because you've got locks on the state, right? So it doesn't matter if they're a little bit late, and you can never get perfect synchronization across distributed systems anyway. You guys know that, right? But as long as everybody executes it at about the same time, then the real piece that you care about is the atomic commitment, and that's the piece that Cerberus essentially deals with, right? So everybody's executed, everybody sends messages to each other in this ephemeral validator set. So you might have 3 different validator sets that are executing this process within this temporary validator set that they're all part of. They all execute, and the execution is atomic because everybody's executing the whole transaction as well, right? In some models, only certain validators execute a piece of the transaction. It's like, well, how can you be sure that there's complete execution correctness across the entire transaction then if you're only executing this little piece based on inputs you've been given from the previous party, right? So you also want...
This is the 3 braid part of the design.
The commitment part is, yeah. So, so essentially, there's a transaction that comes in, and let's just say it's a simple concrete transaction, right? Mm-hmm. That is, it's self-contained. It has no other external dependencies for anything. Yeah, so this transaction comes in. Validators look at this transaction. Okay, I'm responsible for some state that this transaction touches. Mm-hmm. And I know the other validator sets that are responsible for the other pieces of state. So I will expect to receive some messages from them soon, right? Mm-hmm. So some messages go around, and then let's say there's 3 validator sets involved, right? 3 different pieces of state that live in 3 different shards. Yeah. So those validators then form this, temporary validator set that consists of all of them. Mm-hmm. Then they do a state input exchange, right? So it's like, okay, you've got this state that I need, I've got this state that you need, so let's all exchange the state so we can all execute the transaction, right? So you've got this state exchange. Those states that I receive come with quorum certificates, so I know that, unless there is a Byzantine breach in terms of the upper bound of consensus, right? Then providing that there's less than 33% of the network is faulty, I can essentially trust those certificates, right? So I get the state inputs with the last quorum certificate, so I can validate the quorum certificate if I want to ensure that the people that should have voted on it, and I've got a valid state input. So I attach all these state inputs. Then I can execute the transaction. So I execute it, and either the transaction is good or it's bad, right? So let's just assume that it's good. I will then send a vote around to say, I think this transaction is a good transaction. Everybody else is doing the same thing. And if there is 2/3 plus 1 supermajority of votes saying either yay or nay, then I can create a quorum certificate, right, of all of the constituent parties from this temporary validator set. So then I can create a quorum certificate. And with this quorum certificate, I know now that I can commit this transaction. Yeah, and everybody else also has the same quorum certificate because they've generated it too, or received it and validated it. They also know that they can commit it. So then now you can make the assumption that providing that less than 33% of the nodes within the validators within this temporary set are malicious, then everybody is going to commit this at some point, right? Because they are following protocol, they have a valid quorum certificate for some state that's been changed. They're all going to commit it within, some boundary of time, right? Second, 2 seconds, whatever it's like. So then they all commit. They release the locks for the pieces of state that they were responsible for. That temporary validator set disbands, and everybody starts processing other transactions, right? Now you might have thousands of these temporary validator sets at any moment in time, but all of these validator sets, they're just responsible for the pieces of state for a particular transaction, right? If there's another transaction that touches the same piece of state, then that transaction will either also be processed by this temporary validator set, or it will be waiting for the locks on that particular state to be released, right? Now, what's important here, what's interesting is then the failure side of things, right? If I have a transaction that fails, then I still vote, right? I still vote on the transaction, but my vote is a nay. I can't do this, right? The state that doesn't seem valid, or it doesn't execute against the state that I know, or it's just invalid, or the signatures are wrong, or whatever, right? So I'm voting no. And then if everybody, if one of the validator sets can't execute that transaction, but the other two can, then you still have a failure, right? Because you need all of the validator sets to agree with a 2/3 plus 1 supermajority that they can, but only one of the validator sets needs to say no, I can't, with a 1/3. If 1/3 of a particular validator set, 1/3 plus 1 say no, I can't do this, then you can't have a 2/3 supermajority on yes, right? So if that happens, you still have a quorum certificate, but you have a quorum certificate that's yay, nay. And a single nay points the transaction. Everybody who's following protocol will see this quorum certificate says yay, nay. Okay, it needs to be atomic. Everybody needs to agree. You don't have that. So we will record this quorum certificate on Ledger to say that this transaction didn't happen. Maybe there's a failure in a message or something that's been sent around by that validator set as to why it can't be completed. We'll commit the quorum certificate as evidence that we tried, but we couldn't complete. We'll even include the transaction, but we won't change any state. We'll just unlock all the state at this point, and it's all back to its original state before the transaction happened, right?
I have a question about the. I understand that you're putting the certificate. We're actually going to drag you back to something much simpler. I actually maybe we can go back. Maybe we can come back to this, because one of the first questions we have that I think listeners might need to know also is maybe getting you talking a bit about pre-sharding, because this is another area where Radix is different from other approaches, where the way I understand it is you can kind of conceptualize the entire sharding space as, I think I saw one of your blog posts where it's a circle where maybe from the number 0 to 999, it's like 2 to the 256 or something. And, instead of assigning transactions and assigning smart contracts and assigning state to shards, you do something special, which is you say, well, look, we're going to assume that there's this giant kind of like the Bitcoin address space. There's a giant space in which we can have sharding. And if your wallet is this number, you're going to be there. And if the smart contract kind of hashes here, it's there. And then you dynamically, a shard, I'm not sure I'm not exactly sure how you assign the space to shards, but the global state is kind of dynamically managing, so this shard might be this part of the space, and another shard will be this part of the space.
Okay, so early on, it dawned on me that it was much easier to move validators around to occupy the shard space than it was to manipulate the shards themselves, right? So like if I've got a single shard and all the transactions are there, and then I want 2 shards, I then have some logic I need to execute so that, okay, this transaction is now going in that shard and you're going to be responsible for that. And this transaction is going in this shard and you're responsible for that. And all the state and all the smart contracts and all these things, right? And you then have like, if you do it that way, you have this overhead of every time you want to dynamically size up or down the shard, you've got to go through all of this effort of reorganizing, redistributing all of the past transactions so that everybody has the particular state that they need, right?
Yeah.
But we also run into this addressability problem where it's quite complicated if you, as a client, to figure out, well, who's got my transaction? Because last time I was here, it was only 2 shards, but now it's 8. So who has it, right? So the idea that I had was, well, if you just have this state space of 2 to the power 256, then and all of the substate, the state that's the UTXOs, for want of a more accessible term. If I hash the identifiers, then if I get a hash digest out of it, which maps directly to that space. Right? So it's deterministic. So it doesn't matter who or when someone gets my address and I hash it, that's always going to land in the same spot, right? So then to figure out who actually is responsible for that state at any moment in time, all I need to know is a little bit of meta information about how many validators are there, and in the worst case, what was the current shuffle seed? And if I know the current shuffle seed, I know how many validators there are, and I know how many validator sets have been agreed, then it's very easy for me to run the shuffle seed against the algorithm, figure out which validators should be responsible for my deterministic address, right? It's much easier.
This answers one of the questions I was going to come to.
I'm going to give you a very stupid question now.
It's a stupid question.
I love it. I actually
all the time, right? It's like, because you look at some of these other sharding mechanisms, and at any moment in time, you've got to do a lot of heavy lifting, even the clients. I
think it's great. It's one of those things I remember reading about it, thinking about it, and being like, this is the right way of doing things. And it's also the idea that you're doing sharding, but you've got a limit. And it's the fact that you've got the limit in there that lets you do it. Let me ask you a stupid question, though, which is because I actually, something may have explained it. I may have just missed it. We're taking the quorum certificates and we're taking, either it's yay, 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 or yay, nay. We're adding it to a ledger for the shard. What I don't understand is, we're adding it apparently to a linear blockchain in the shard. Does that mean that if let's say one of the shards is 0 to 15% of the hash, does that mean that there's a blockchain for that shard, or are we some kind of approach? Because there are approaches where like every address has its own blockchain. When the transactions are committed in the shard, and some of the docs say they go into a block, what is that?
Okay. So these aren't stupid questions. These are really good questions, right? So let's say you've got a single chain, right? A single shard, right? So you've just got a single chain, for want of a better word. Everybody understands chain. So you've got a single chain. It's unsharded right now, right? But then that chain is at capacity, So it can't handle much more throughput, if any. There's a lot of validators there because people are joining the network. A lot of these validators are monitoring their resource usage, right? And so let's say that, 2/3 plus one of them or more are, okay, right, I'm getting to the point now where I'm about to lose resource, right? I'm CPU's high, memory's high, bandwidth is getting maxed out. I'm going to suggest to the network that we we add another validator set, right? So someone can propose that, and if you're in that particular situation, you probably get quite a few proposals from different validators saying, "Hey guys, can we scale up the number of validator sets?" Right? And so everybody will vote on those proposals, and if one of those proposals has a 2/3 plus 1 majority agreement between all the validators in the network, yeah, so there's a consensus around scaling up, scaling down. Then they will all agree on maybe the next epoch or the epoch after that to scale up, right? Now, the way that this mechanism works is that we've already got this fixed kind of state address, right? So that doesn't change, yeah? Everything still just lives in the same spot that it was in, right? But what we do is we split the validators in two, and the chain on the transition into the next epoch, the chain splits into two, right? So you now have two validator sets.
Right.
So validator set 1 builds this chain, and validator set 2 builds that chain, but they both have a common point.
So it's a tree, the uncharted or the totally new blockchain. You've got one chain, and then when it dynamically shards, it splits, and then when one of those will split.
Yeah.
Okay.
But
So
you can get another way as well, right? So you can say, okay, you can converge as well.
Go ahead, please.
Okay, so let's say that I'm now underutilized, right? CPU's at 10%.
Yeah.
Some validators maybe have left, or maybe we still have a lot of validators and stuff, but I'm underutilized, right? So I and others can propose, hey, I'm underutilized. I'm not seeing as many transactions. My profitability as a validator is low. Whatever. Yeah. Should we scale that down again? And so you can do the same mechanism works. Put a proposal out. Everybody, if enough.
Yeah, you're right. It's the tokens won't be on both chains, so you can merge them.
And so then, or the tips of this tree.
Because they've got a common fork ancestor. Yeah.
They have a common ancestor as well.
It must resolve back because you can't have
So you can reduce too.
So
that answers the question. What I was wondering is if you're shuffling, because the mechanism in global state, you're also shuffling validators between shards. And so I was wondering, the commitments are going somewhere. How are they actually syncing the blockchain? Where are they going? How does that work?
Yeah.
Thank you, Richard.
With shuffling, obviously you do want to shuffle your validators around, because if you are in the position where you have some validators that have a influence in a particular validator set that is serving a portion of this state space, you want to break that influence at some point, right? Maybe it's not enough influence to be malicious, but it might be enough influence to maybe censor some transactions or cause some very short liveness breaks for things, front running, all that kind of stuff, right?
But that shuffling is deterministic though, because you need to be able to tell.
Yeah. Shuffling is deterministic. Yeah.
Who's going to be in charge of what?
Who's going where? Right.
Where? Right.
Yeah.
Well, go ahead, please.
Right. So every epoch, there's another total round of consensus, and it's basically a shared coin flip. You can get an idea how this works if you read up on Ben Orr's shared the shared coin stuff. If any of your listeners are interested in that, but essentially there's a global round of consensus that agrees the seed, and the reason it's done globally is that even if 99% of the network is dishonest, if you have one honest member of the network that actually produces a random number, then the output is random, right? So you have this kind of global round of consensus every epoch. It just happens in the background, so that it doesn't have to be immediate. Where you agree the seed for the next epoch, and then there's an algorithm that determines which validators are going to shuffle out to somewhere else, which validators are going to stay where they are, because you don't want to shuffle everybody, right? You just want to shuffle a few, because if you shuffle too many, then you'll have liveness disruption in particular shards. Right? So
I have a question on this. I was going to hold off, but we're on the topic. I know that in other sharding designs, with things like switching validators between shards, people do things like they pull them off, and it's like, okay, well, you're pulled off of this one, and you're going to be assigned to this other shard. And there's this period of time in which people aren't paid. What I'm wondering is, you're deep in the sharding space. Is this just to provide them with a time to sync the data? Or is there some attack that is being addressed with these kind of techniques? And regardless, how does Radix deal with this? Is there this time period where if I'm a validator or I'm switched, I'm given an epoch to get myself resynced to the chain? Or what are the issues here? And do you guys handle them in a different way than other designs?
So I handle that differently as well. If I'm moving from this validator set to a different one, then I need to resync, right? Because the state that I currently have is relevant to this section of the state space, and I'm moving somewhere else, right? So I need to resync state. And usually in a lot of sharding models, what happens is, okay, you're moving and you've got an epoch to sync up, and then on the epoch after that, if you synced in time, then you can start to participate again, right? But the mechanism here is, I know an epoch ahead where I'm going to go, because there's the agreement of who is going to move, and then on the next epoch, that's when those that need to move, right? So what I can actually do is that I can get ahead of my syncing a little bit. So all I actually need to be able to participate in consensus is a snapshot of the latest state. I don't need the history, right? I just need the latest state. So I can, prior to me moving in the next epoch, I can ask the validators in the set where I'm moving to, can you send me the current snapshot? I receive the snapshot, and that snapshot will be close enough to current real time when I actually move that I'll be able to participate in most transactions, right? So if I ask for it, say, an hour before, I'm going to miss about an hour of state, but I've still got enough state to be able to participate in 95% of the transactions, right? Then when I actually move, I can then sync the history or a pruned version of the history, my snapshot.
The size of that should be reasonable because it's dependent on the capacity of the validators to handle data, which will influence when they scale up. So the validators in that particular in a validator set are keeping an up-to-date copy of the snapshot, right? Yeah. So ahead of time, I can contact some of those validators in the set I'm going to move to. How big is the snapshot? All right, it's 500 meg. Okay, I can download that in 15 minutes. So an hour before I move, I'll ask you for that snapshot, right? And then I've got the snapshot that I need to participate in most transactions. If I'm participating in most transactions, I'm keeping most of that snapshot up to date. And then as I'm syncing the history or the history that I need, I'll fill in the 5% of the gap. And by the time I'm synchronized, I have the complete snapshot, right? I have the complete history up to now. And so I don't need to wait an epoch or sync over an epoch. I can kind of get ahead of it to a large degree so that I'm not just sitting around doing nothing and just syncing for hours, right? I can still add value.
I was asking because it relates to the economics of incentives, and it's an area where I think people don't usually talk about it. Thank you for the answer.
There is one other piece as well, actually. In a lot of cases, the way that the state model works, and the way, because remember I mentioned earlier on that when I'm in a temporary validator set comprising of more than one, there's this state exchange, right? So if I don't have the snapshot or enough of the snapshot for me to be able to participate, I can ask other validators, hey, I don't have this piece of state that I need. Can you send it to me? So, and I get the state for the other validator sets, they send it anyway, right? So even if I don't have a complete snapshot of the state, in many cases, I get given the state that I need anyway. So I can still execute, I can still focus. It's only in cases where it's a non-concrete transaction where I'm likely to run into issues. Hence why 95% of transactions I can take part in. And non-concrete is where I look at a transaction and I'm able to determine that, I need these two pieces of state. Then there's a smart contract called, but there's a conditional in that smart contract that either does A or B, right? And A or B may be to call this smart contract over here in shard 25, or this smart contract over here in shard 12, right? And I don't know what that's going to be ahead of time of execution, right? So in those cases, those non-concrete transactions, if I don't have a complete copy of the state snapshot, then I may not be able to either determine what the next, what this kind of on a conditional, what smart contract is going to be called next, and what do I need. So I may just have to back out of those kind of non-concrete but complex executions. But all the simple stuff, I'll either have all the state that I need, or I can be given all the state that I need. So
you have any questions, Richard? I can ask another really simple one.
Go for it, because I've had a couple of mine answered by the conversation. Because I was worried, for instance, about like with that syncing, how you would keep it to a sane size, but the logic would be.
The problem with syncing is the history, right? It's not so much the current state; it's the history that takes the time.
Yeah.
So if there's a mechanism where I can just grab most of the state which is up to date,
well, I just think checkpoints, and I'm kind of thinking, okay, state, you're syncing it. I was more. The look at the switch is interesting. I'm also assuming there's a difference between like the UTXO state and EVM state or VM state. I know that Cerberus has those 3 levels of increasing complexity. I'm kind of assuming that the first one is for UTXO and the other 2 are for smart contract related.
That's for you're talking about O Cerberus and P Cerberus and stuff, right? So
yes,
that's the model.
Like increasing levels of paranoia in the consensus.
Right. Yeah. So that's just from the consensus mechanism that regulates the kind of cross-tick if you want to be, and you can assume that everybody is honest. Yeah. But if you do that and it turns out that they aren't,
are the decisions about the level of trustlessness made by the people who are making the transaction, or is it based on the kind of transaction that's being made? Like if I'm sending, just because I was thinking, this could be totally wrong, so please, I was thinking that maybe like the UTXO, because UTXO are very basic, might be the simplest and it's the most efficient. But then as soon as you get to smart contracts where maybe there's an external form of value, you could have double spending. Do you want to comment on this? Do the transactions actually get to say, look, I'm paranoid, I want paranoid Cerberus for this transaction, even if it's a very simple cross-shard one?
So the different models of Cerberus were really just to give a full explanation and full detail of how you can go from a very like a crash tolerant Cerberus to a optimistic Byzantine tolerance Cerberus to a pessimistic Byzantine tolerance Cerberus, right? So in terms of the transaction themselves, that doesn't really have any bearing on the transaction. It more deals with the efficiency of consensus, right? So with optimistic Cerberus, if you don't have any Byzantine actors in the system, then it can operate very quickly, because it's able to make these assumptions, and providing those assumptions.
It's the speed of the message. So are you guys an implementation of the most pessimistic, or is there, who has the ability to choose the level of messaging?
There is no choice. So in the case of a permissionless network, you would go the pessimistic Cerberus route, right?
Okay.
So you kind of limit, you take some off efficiency a little bit, but your resiliency goes up, right? You're able to react very quickly to Byzantine and give a very strong safety guarantee, right? But if you were in a permissioned environment where there is some administration that gives the authority for validators to join, to be part, or a federated system, then you could probably choose optimistic, right? Because if there is a failure, there's somebody in charge that can take action to deal with that failure, right? Whereas in a permissionless, it's much more difficult.
Got it. Let me pull you back to the simple question, which is, you talked before about how you've got some level of superficial state where if I'm a user and I know my address, I'm going to be able to figure out, Alice is sending something to Bob, so I know which two shards this affects, and I can send the transaction in presumably to those validators directly. Does data work in the same way in reverse, where if I'm a user and I'm interacting with a smart contract, I'm going to find the validator on that shard and pull data from them? Or, is there something where is there a network-wide level of data distribution and a shard-specific level of data distribution? I don't know the answer, which is why this is the question.
So
really think about it.
You can do the same thing with data as well, right? So if you push some data into this network architecture, then that data will live on a shard somewhere, right? And depending on excuse me, guys, sorry. No, so you can store data in the network as well, and your data will have a specific address in that circle of state, right? But there's also two other interesting things with this model that I think is important to understand that you probably haven't seen anywhere else. So all transactions are cross-shard, right? So even if I'm just
all transactions are
cross-shard. Everything is a cross-shard transaction. Everything.
Okay.
Right? And the reason for that is this. So let's just take a simple blob of data that I'm putting on the ledger, right? That blob of data will still be a cross-shard transaction because you've got the blob of data, but then you've also got the record of the transaction that blob of data was contained within, right? So the blob of data has its own hash, which you can translate to a slot in that state space, but the transaction itself also has its own hash, right? It's the transaction that's hashing the blob plus any other metadata that's in there, right? So that also has its own slot in state space, right? So in that sense, everything, or at least almost everything, unless those two hashes just happen to sit within the same shard, is cross-shard. Now, there's something else that I can do here. If I'm a user, I can say, I'm making this simple transaction, but I'm paranoid, so I would actually like this to be validated by more than the minimum amount of validator sets that's required, right? So in the case for this piece of data, if I'm paranoid, or I want to make sure that this data is always available no matter what happens in the network, I can say, instead of it just going to 2 validator sets, I want it to go to 10 or 20 or 30 or however many there are, right? There's an increased fee associated with doing that, but then you'll have a much larger validator set comprised of all these other sub-validator sets which are validating that transaction, right? So you get two things from that. One, you get redundant copies of this piece of data all over the network. And number two, you have an increased amount of economic security from the stake back in this blob, right? So you go to the final point. Because everything or almost everything is cross-shard, you can also reconstruct 96% of all the transactions that ever happen. So if I lose shard 10, right, I can go to all of the shards and say,
the right array.
Have you guys got anything that touched shard 10 at any point in history? And they'll all go, yeah, I've got this, and I've got this, and I've got this, and I've got this. and the core certificate can also contains like things like the block header and a bunch of other meta information. So I can essentially reconstruct at least the state, if not the history. I can reconstruct all of the state for shard 10 that completely disappeared off the face of the earth almost entirely because I have redundant copies of all this stuff in all these other shards.
Things like transactions where I sent something to myself would be irrelevant anyway because I didn't change the net state. Like that would definitely be on the same shard, but it wouldn't.
Yeah, but even if you did do
it's got
that,
zero
right,
effect. Right?
It's the zero effect, but the transaction hash might not be in your shard, right? So there'll be a
Right.
record of that transaction that lives somewhere else. You've sent $1 million out back to yourself again, right?
Yeah. You have any questions, Richard? I don't know if I've exhausted my stupid questions, but this has been really helpful, actually.
These are great stupid questions because they're not stupid.
Actually, for me, the missing piece was the that it's challenging with docs because you've got a lot of new language and you've got a lot of new concepts, and I think you have the same challenge we have, that when people approach the network design, they see a word and they're like, okay, well, I must understand this, and then the more you read on, the more it's kind of like the ground gets
and get to the wrong definition, right?
Well, even just a term like shard had me thinking traditionally or much closer to sidechains because most of the models I've looked at are in that way, which meant I had a bunch of questions in here that dissolved
really
when I came to understand.
Right. But then everybody knows what a shard is, so
One thing I mean,
a shard than what it is, because like if you say there's 15 validator sets, well, what does that mean then? It's like there's 15 shards. Oh, okay, I get it, right? And it's just
there's 15 validator sets spread across the potential state space matrix.
The state space, right? Well, you go on crypto Twitter and say that, so you can have unlimited validator sets that are distributed around this state space. What's that? It's basically shards. Oh, okay, I get it. It's like, but then
we have similar things with
confusion on the other side,
question. We've got people who are listening on the Swarmcast, and we've got a chat. If you click in the top, if you're in the show, you get a little panel.
I can see. I got how guys. We really want to attend.
I was just going to suggest, if anyone listening has a question, please. I think this is a great point to come in and fire away with it, because I've actually had my questions answered. This was super helpful. Richard, if you've got any more. Otherwise, if you're listening, anything you want to throw at Dan, please.
I think we wanted to keep time to about an hour, so we've got a few minutes and good questions we can handle. Otherwise, we can wind up. But let us know.
I'd be curious, Dan. I mean, is there anything we have? Well, there's a ton we haven't asked you. Is there anything that you should tell us that we should ask you that we haven't because we haven't? That you think
I think from a purely understanding the sharding architecture of Radix, I think we've actually done a really good job in this session, right? Yeah. Obviously, there's a lot more beneath that, right? Because you have Cerberus that is responsible for the cross-shard communications, but validator set communications, really, right? Yep. But then those validators themselves, they also need to have a local consensus, so that they can agree on, okay, what are we going to process next, right? Regardless of all of these temporary sets that we're in, we need to come to agreement locally that all of us in this validator set agree on this quorum certificate, or we are agreeing to take part in validating this transaction, right? Because, for example, I can send a transaction with an invalid signature, and that validator set has to agree that, well, we're not going to process this. Even if these other validator sets decide they do, from our perspective, the signature is invalid. So we're not going to include this in any of our proposals. And if we don't include it in any of our proposals, then we will never vote on it. And if we never vote on it, then the quorum certificate that gets generated by those other validator sets, they won't have any votes from us. And so therefore it's a rejection, right? Because of the yay and nay, the emission of
empty vertex, or failed message.
Right. Yeah. So it's like, yeah, I know we're involved in this temporary validator set with you two guys on this transaction, but the signature didn't verify, so we're going to vote no anyway, right? We're not even going to bother to execute it. We're just going to vote no. But your local sets of validation, right? So you need that local consensus as well, and the local consensus stuff is mainly what my work on Cassandra has been, right? With the motivation of like essentially, you guys know consensus, right? Like typically, if you want a strong safety guarantee, such as deterministic consensus, where you've got validators voting and stuff, you can't have a liveness guarantee of any kind under asynchrony, right? But if you want to have a liveness guarantee at all times, such as Nakamoto consensus, even under asynchrony, then you have a weaker safety guarantee, or in the case of Nakamoto, probabilistic, right? But when you have a network that potentially is serving millions of transactions a second with, thousands or tens of thousands of validator sets, if you've only got a strong safety guarantee and a liveness guarantee under synchrony, what happens if some of the shards go down, some of the validator sets go down, right? Or you have a liveness break. How do you get it restarted again? But you're going to have a conference call with 100,000 validator operators. It's just not feasible to do that, right? So the Cassandra work I've been doing is, how do you have a kind of nicely integrated, elegant pipeline consensus mechanism that under synchrony gives you obviously liveness and a strong safety guarantee, but under asynchrony it maintains the strong safety guarantee of the last thing that was committed under synchrony, but under asynchrony it gives you a weak liveness guarantee and you have probabilistic safety, right? And then how do you use those two properties, depending on what synchronous state you're in, to either, be in a nice healthy condition or get back to a nice healthy condition, right? And to get back to a nice healthy condition in an autonomous way, you need some kind of liveness guarantee, right? Even if the only thing you're doing under that liveness guarantee is, say, slashing, right? We're slashing. If that's all you can do, but it gets the network back to a healthy state, then that's enough. And you don't have to have a conference call with, however many validators that are in the network. And then the other motivation for Cassandra was, how do you have a local consensus mechanism that is extremely performant?
We should look into Cassandra and have you back in the future. Two questions about Cassandra. We can make a
now that we've got the fundamentals down. I got to read.
You guys have our ecosystem. There's the the Appler engine and the VM, and I think today we were focusing on sharding because, to be honest, when we look at Radix, this is where we try to.
Everybody knows
where my attention is.
Sharding, right? But there's also the complete stack, the Scripto, the Radix engine, all the user experience stuff, the developer experience stuff, Cassandra, Sharding, all these things. It's quite a monster when you look at the whole thing. You kind of have to step back a little bit.
Yeah,
it is better to try and just pick through them one at a time than try and do it all in one go.
Yeah, initially I was quite interested in Scripto, but I kind of held back on getting into that too much because I was trying to get my head around some of the more fundamental issues we discussed here.
Where are the blocks? How are the blocks?
Where does the data go?
Yeah. So they're not strictly blocks. They're but at the same time there is like this record of order of things that have been processed.
Yep.
But really, what you have is you have this local order, and then you have a global order for things that conflict with each other. But then what sits atop of that is this kind of directed acyclic graph of all the state transitions, right? So it's kind of multi-layered.
It's complicated. I mean, I'm not quite sure. I know the shards have their own. They have their own validator sets, and then there's the leader. Then the leader, I think, is in the global validator set, and what do the leaders do? And what
that's
do the
another thing
validators
you see
do?
with Cassandra was to get rid of the leader aspect. So Cassandra is leaderless as well, because if you fall into a liveness situation and your leader is in the subset of validators that have disappeared, then doing view changes and electing new leaders and stuff is complicated, right? And you can end up in a position where you can have a large amount of latency between the leader disappearing and you electing a leader that's actually present, right? So having a leaderless kind of mechanism in the same way that Bitcoin does, that was also one of the motivations for the Cassandra consensus stuff. So Cassandra consensus is really interesting when you dig down deep into it. It's like it's a rabbit hole all of its own.
Richard, you have anything? If not, why don't we call it, because it's been about an hour. Dan, I hope we can get you back in the future and ask you a combination of good questions and more stupid questions. If people have been listening, hopefully this is useful for others as well.
Hope so.
The random subset that are like us and what they don't understand about Radix and what they do. But if not, thank you for coming.
And
I would love to come back on. We can make it a somewhat regular thing, and we can get into all these different topics.
Next time we can
give me like a whip head up.
We know that the video works with 3 people now. It was touch and go for a bit, I think. We could do it with beer
because it's peer-to-peer. It's genuinely dependent on each person's connection to each other. So it does results can vary, but I think it's come off well. So.
I like this you guys have built. It's super cool, actually. I'll start to use it a little bit for some of my own stuff. And
it's free and permissionless. So
report the bug. Let us know when it breaks. That's what we need to know.
The cost is badgering us about any problem.
If Radix breaks, I'll let you know. I'll send you an email letting you know that my transaction has not gone through, and I demand service.
Exchange bug reports. That's brilliant.
All right. Well, thanks, Dan.
Okay.
Always my pleasure. It's been a great conversation.